As you probably already know, what inspired the topic of the Ausglass conference this year was that it's the UNESCO Year of Light. And we thought, what a beautiful topic for a conference. So our first day here, we've had a loose theme of light as material. And light is such an amazing, intangible material that defines everything that is visible to us, how we experience all our surroundings. But what are we seeing? And I think John Burgess puts the question beautifully, and that is the relationship between what we see and what we know is never settled. Each evening we see the sunset. We know the earth is turning away from it, yet the knowledge, the explanation never quite fits the sight. And I really like that gap between our mind and our eyes. So in this session, Sensing the Unseen, we explore the unseen world. And first speaker we'll have is Catherine Truman, who is a very well-known artist, trained jeweller that makes work about the body. She is in all the major museums and museums overseas. I first came across her work in the Victorian Museum of Victoria, where I had to do a Year 12 art assignment on one of her installation pieces. So I can't quite believe now that I'm introducing you. It's quite an honour. She was invited by Professor Ian Gibbins to be an artist in residence in the Autonomic Neurotransmission Lab at Flinders University. And this is a project that he initiated, getting an artist into a science lab. And this collaboration together led on to a new collaboration called the Miroscope project, which will be explained later. Ian is a neuroscientist who researched the structure and function of nerves that control our organs. And he did this by using microscopes. And the microscopes are like our tools and like our eyes. And these amazing equipment that you've been working with for probably over 30 years were being replaced by the university, being decommissioned. And they thought, this is not something that's just going to go on the trash heap. These bits of equipment have a new life, and that's where the Miroscope project formed. Our next speaker is Heike Ebendorff-Heidepriem. She is an adjunct professor at IPAS, and some of you lucky people have already had a tour of IPAS, and it's an amazing institution. Amazing. She's responsible for making glass extrusions with tiny, complex structures in them, holes, through the extrusions. And the extrusions of glass are just as wide as one single hair. And through these amazing structures, we can measure some amazing things. And two examples which blew my mind away. Well, firstly, it was from the wine industry, because I'm a little bit connected to the wine industry through my partner. But to be able to measure what's going on inside a barrel without ever opening the plug. So this is a line, a small, the invasion line is only as wide as a hair, and that can revolutionise winemaking. Probably even more importantly is another project that she is working on is with IVF, and that is towards testing the health of an embryo before it is implanted into the womb. And so we are delighted to have you and most excited. And thank you very much. We'll have questions. We'll do the speakers one at a time, and then we'll have a question session at the end. Please welcome.
Hello, is that better? Can you hear me? Is that loud enough? I'm really delighted to be here today talking at a glass conference. This is the first for me. I've talked at all sorts of other conferences, but not glass. And I'm very interested in the differences between the mediums and people's attitudes to both technique and concept. So this is a real eye-opener, especially after the last talk, which was just fantastic. So I met Ian in 2007 when we both participated in a public forum called With the Body and Mind at Flinders University. We're both very curious about the ways that the human body is represented through art and science. And Ian readily welcomed me into both the medical school and to the community of his neuroscience lab. And over the years, we've consistently collaborated on some really wonderful and very fruitful projects, both from an art perspective and a science perspective. But last year, we collaborated on the Miroscope project, and that was developed over an entire year and culminated in a major exhibition at Flinders University City Gallery in Adelaide, and we had a dream team of curators and artists. When I was asked to speak today about this particular project, I wondered how on earth I was going to neatly summarise it in relationship to the themes of this conference. I just wanted to give you a taste of the outcomes of that project first, and just show you some of the work that was in it. We had installations and objects. This is Angela Valamanesh's work. Nicholas Follen's work, which is an extraordinary working still. And we made films. This is a manual from one of the microscopes. It took about an hour to actually turn the pages of it for the film. And we even had a spinning chandelier, all made from and inspired by a suite of decommissioned microscopes. Believe it or not, this is a microscope. I think these outcomes are actually testimony to a rich set of experiences that were shared by all the participants. And Ian will talk more about that in a minute. But today, what I'm really interested in attempting at least, is to give you an impression of the more ephemeral aspects of that project, the aspects that underpinned the project and the evolution of it, the thinking, the experimentation, the invention and reinvention, and the curiosity that actually drove the work, because I don't think that's talked about enough. So, and I know as time is of the essence, I'm going to direct my attention to the generation of one particular work that I made. And I believe on Sunday, Deb Jones, who was one of the participants of this project, will also talk about some of her experiences. So, firstly, some context. A couple of years ago, when I was up at Flinders Uni, Ian drew my attention to a massive bit of complicated machinery that was wedged in the corridor off the microscopy suite. And he said it was about to be decommissioned, most likely scrapped. And not only that there were more. And interestingly, that they represented the transition from the electromechanical microscopes of the 1970s to the more fully electronic instrumentation that we now have. So both of us were really keen to see if we could give them another life, as Jess has just said. And so we hatched a plot, and the microscope project was born. Our overarching theme was to reimagine them somehow, to invoke their underlying technology, their scientific history, and the social framework, and importantly, to explore the strong relationship that we had already developed between the ways that artists and scientists both question the world. First off, we needed a base to house the microscopes and all the paraphernalia that Ian had gathered, a place to think and work and talk. And so, with the aid of some welcome funding, we leased an old eucalyptus distillery on the banks of the River Torrens here in Adelaide. And it was indeed the lingering scent of eucalyptus that permeated the entire project. For practicality's sake and ease of transport, Ian had actually dismantled a significant portion of the instruments. So when we arrived, we unpacked and laid each component out on trestle tables. And also strewn around the room were some more intact instruments and boxes of manuals and all sorts of fantastic stuff. But for the occasional miraculous lens or eyepiece, most of what lay before us could have come from any refined machine. And this is how we began. With no anchor, we all drifted about this strange aromatic room, bobbing amongst a sea of complex fragments, all seemingly awaiting a new purpose to be given meaning again. And in this next shot here, those big grey shapes are actually the old eucalyptus vats. So it was a great atmosphere. Ian was the only one who knew these instruments inside and out. So he was both assembler and disassembler, and always our first port of call for information. What is this? What does it do? How does it work? But his answers only ever stuck for seconds, just long enough to be obliterated by the next lot of intricate explanations. This went on for several weeks, until eventually it dawned on us that there were stories embedded in these fragments. Stories of human endeavour. That these were products of human ingenuity, designed and made and used by individuals in order to see things not available to the naked eye. Who made them? Who were the original assemblers? And how did they actually interact with this machinery? And so gradually, as we all began to find our way into the project, I remembered two really important things I'd learnt whilst working in scientific environments over the years. Firstly, it's the vast unknown that moves you forward. And secondly, that failure is just an interesting incident on the way to somewhere else. We are curious beings. We are led by sight and we confirm by touch. How else could we understand anything outside of ourselves? It's what defines us as human. The ways we satisfy this curiosity through art and science are what drive my practice. So engineered to look through matter or along its surfaces, the microscope augments our sight and to a certain extent our touch, so we can pursue a line of inquiry. These implements have actually taught me a hell of a lot. They've given me a critical experience of immersion, a sense of the vast, a sense of the unknown. I clearly remember the experience of being in a darkened room up at the university one day with a confocal microscope, and the swimming sensation when I've looked into this glass screen, staring at one of a million images of a minute part of the surface of one cell, captured in a millisecond of time, and Ian leaping about exclaiming, "No one's ever seen this before." And I said, "What?" But that sense of discovery is addictive for both artists and scientists. So, ensconced in the distillery, immersed in this sea of complicated objects, I wondered then, where do we, quite literally our bodies, my body, where do we begin and end in our interactions with these miraculous instruments? Do these machines perform us, or do we have a more embodied control over how they operate? I began with space in between, but it's a really hard place to put into words. I felt I had to strip back the relationship, and even though a considerable number of the works were made in collaboration for this project, particularly with Deb and Ian, in a sense, I, like the others, had to begin alone. And it was an extraordinary place to start. In moments of solitude, I would simply wander the space and move things from one table to the next, change the order of the parts, run my hands over the control panels, imagine what I might see through the lens, on the screens, what might light up, where the energy would come from. It wasn't a really complex, conscious process, but I was very aware of my hands being the mediators. I felt driven by a sense of endeavour, a mixture of complete uncertainty and calm. At the same time in my studio, I had begun to experiment with thermoplastic, to explore the material as far as I could stretch it. I'd heat the white transparent rods and stretch it as far as I could, and this seems to be how I move forward nowadays in my work. And early on in the process, I picked up a pair of white cotton gloves that were lying on my bench, and, well, here's my artist statement written for the exhibition to give you a taste of the process behind a series of images I called Sensate Gloves. The making of Sensate Gloves. It's easier if I wear the glove whilst adding the filaments. A pristine white cotton glove, the kind conservators and collectors wear, the same white as a researcher's coat, ritually worn to protect the object you're touching, not you. They act as a kind of soft mediator. The filaments are made of thermoplastic. I touch the hot plastic to my fingertip and it bonds with the weave. Then, with careful measure, I draw out the thread like a hot glass stringer, like a stretched tendon, like a nerve ending, until it tapers and thins and breaks, forming a long, fine, flexing, trembling filament that amplifies with every nuanced flick of my fingers, both beautiful and macabre at once. They bridge the they bridge the distance, extend my touch. They become like smoke in the light, both radar and sonar, and refine my line of inquiry. So in these images, I'm both the performer and the photographer. No mean feat, I can tell you. But they are a very private, now public study of what I experienced as the barely sensed. They are the remaining documents of some very subtle investigations between me and those miraculous instruments and the potential between us. Taken in the very early morning light and the evening light in an old eucalyptus distillery, they are 1,000,000 miles away from their origin. And through experience, I've grown quite comfortable with the notion that these images will forever and always be incomplete. Thank you. And next is Ian.
We're just waiting for those to change over. A bit higher. I'd also like to thank the organisers for inviting me to speak here to a bunch of glass people. I hadn't really thought of myself as being a glass person until the Miroscope project, in a way, where glass is a significant component of a lot of the materials that we're looking at. But a lot of what we're looking at as well, we're electron microscopes. And almost by definition, they don't use light and don't use glass. So when I was asked to speak here, I thought, what are we going to talk about? And the part of my things I do is a lot of writing, and I thought, well, let's look at the language of all this stuff. And how does the language that we use to describe these instruments, the processes that we use, the way in which they work, what's that telling us about the way we interact with those instruments and the way that they interact with us, following on from the sorts of concerns and interests that Catherine made? So I want to talk about, there's the metaphor of glass. And glass is the core technology of an optical microscope, a conventional microscope, the sort of instruments that most people think of as being a microscope. There are glass lenses, there are glass mirrors, there are glass prisms, there are glass filters of various sorts. But they're mostly hidden from view. This is the shell of a microscope, and all of the glass has been taken out of it, and all the controls for those pieces of glass. And then in common language, we know what these properties of glass are like, and they're used to describe all sorts of things. It's as clear as glass. Hopefully as clear as the high fluorite lenses, which are part of these microscopes. As smooth as glass. Hopefully as smooth as the perfect optical surfaces that are on the lenses and the mirrors that we use. Talk about someone having a glassy look, being sterile or a bit aseptic, like the glass that's used in many of the biological microscopes. You use glass because you can sterilise it. That's an important component. There are metaphors of light as well. So one way we refer to these microscopes commonly is just they're light microscopes, almost as though they're made of light. And it's so embedded in the way we think about the operation of the instruments that if you ask most scientists, I wouldn't even think about it. What are you talking about? But it's the same sort of language that we use in day-to-day life as all the time. We shed light on something. We illuminate an idea. We become enlightened, as people have said this morning. And then you have light-hearted. Sure, that means light, as in not heavy. Yes, but if you look at medieval paintings, the hearts of saints are usually a fire with some sort of flame with light emanating from their hearts. It's the same sort of word. And of course, you have the absence of light being something negative, being in the dark, being in a dark mood. And then we have dark field microscopes, which people usually hate using because they're so hard to get to work properly. So, a little bit of physics. You probably heard this at the talk over lunchtime. So, light behaves in different ways depending how you look at it and how you use it. And I've been born and bred a scientist in a whole lot of different disciplines. I suspect that the deep nature of light is impossible to know in any real sense. And part of the problem is the way we describe light. Sometimes it's particles, sometimes it's waves. So the particles are photons, which are the components of light which interact with matter. And what's going on here? It's the stuff which gave Richard Feynman his Nobel Prize, the strange theory of light and matter, how the photons interact with the subatomic components of matter. You think this is all airy-fairy sort of stuff? The last work I was doing before I retired was doing imaging with single photons, counting single photons and building up images out of the single particles of light. Quantum mechanics might be impossible to understand, but you can still use it. And then on the other hand, light can behave as waves. And sort of the mass behaviour of light can be explained by waves. And you use basically wave theory of light to figure out the optical parts through a light microscope. And then, of course, colour we described either with particles, the energy of the photons, or with waves, the wavelength of the light. Glass in a light microscope is used in, as I said before, in lots of different ways. One way is to focus the light. That's what lenses do, of course. But it's a complex process. And one of the things which was amazing during the microscope project was actually pulling apart things I was never ever allowed to touch when I was using them. And so the complex lens systems, ideally, they should give you magnification without distortion, without any sort of aberration. But that's impossible. It's a physical impossibility. There's always something wrong with your image. It goes back to what Catherine was saying. How do we interpret what it is that we're seeing? And even the best corrected lenses, which might cost you these days $40,000, $50,000 for one of those lenses up there, modern versions of those, still have aberrations in them. And if you're working with single photon imaging, you have to know those aberrations. You have to know how each photon's going to get thrown off track by those lenses. Traditional light sources, like the one down the bottom there, are housed in glass. It's light as a container. So what are we containing? In a light bulb, or an incandescent bulb, you have your tungsten filament from which the light's emitted, and in that space between the glass and the filament, you have some sort of inert gas, which improves the lifetime of the filament, makes the lights brighter. That lamp there is actually a high-pressure mercury lamp. It works at very, very high pressure, very, very high temperature, and the glass there is special glass, it's special quartz glass, which can withstand those high pressures, those high temperatures, and also transmit very high levels of ultraviolet, high energy light, which normal glass won't do. So glass houses the light in a way. But what do you see? It depends on the knowledge of the optical path as much as the knowledge of the specimens that you're looking at. Glass in a light microscope also supports what it is that you're looking at, and it shields and protects what it is that you're looking at. So glass is a support, glass is a shield. I can't point to it. At the bottom there, we have glass cover slips, which support little pieces of tissue you put on the microscope. And above them, you have little cover slips, 0.17 millimetre thick glass that protects the specimen from oxidation, from dust, and hopefully not too much from the lenses of the microscopes which are coming close to them. They need to be flat, they need to be clear, they need to be strong. It's the protection we seek, it's the requirements for moments of separation. So here's the electron microscope. This is one of the ones which Catherine had in her images. This is at the still. This is the E-Tech microscope. So in an electron microscope, you're using electrons rather than photons. It's a beam of electrons. And then you have to use them to generate your image. Why should you do that? Well, you get much, much higher magnification. Ultimately, you get down to atomic resolution with an electron microscope. Not that one, but the subsequent generations of microscopes get down to atomic resolution. They've just bought one over at Monash for $20 million or something. These systems work under very, very high vacuum. They work under very, very high voltages. But it's a trick to get them to work. You have to find the balance point. You've got to turn the dials this way and that. And so here's one of the other electron microscopes. This is the control unit for one of them that we used in the exhibition. And this notion of the metaphors of glass, the metaphors of light, are used in an electron microscope in different ways. So you have the functional metaphors of the technology. These microscopes, this is just the control unit for it, you have lenses, and they're the same sorts of lenses that you have in a light microscope. You have objective lenses, condenser lenses, dispersive lenses, all using exactly the same names as you would if they were using light, but they're using electrons. You have an electron beam, which you focus, and that beam has brightness. No, it doesn't. It's just a beam of electrons. But when you use it, it behaves as though it's got brightness, and we use exactly the same term. And you can scan that beam. And then you have the source of electrons in a traditional electron microscope like these. The source is just a souped up one of them. It's an incandescent light. It's a tungsten filament in a high vacuum with a lot of electricity going through it, spewing off electrons rather than light. So this is what an electron lens looks like. Sort of. It's been tapped a little bit. And the electron optics are essentially massive electromagnets. And through the centre of that coil is a tiny aperture through which electrons go. That piece would weigh about 20 kilos. It's about that big. And so these lenses bend the electron beam and focus the electron beam like waterfalls going to an oasis. And as a user, you can only guess really what's going on in there. You hope it's working correctly, but maybe not. But then in these older microscopes in particular, these ones that we pulled apart, there's a heart of glass. And it's built around electron tubes. And to quote the manual that we had, the electron tube is a marvellous device. That's the opening line of a manual RCA electric vacuum tubes. And what do these things do? Well, in the early microscopes, the amplifiers and things were valve amplifiers. If you're a hi-fi person, you might still be interested in those. But then there's the sensation of glass as well. The instruments, you have to know what's going on inside the instrument. And you have to be able to somehow or other turn the electron beam into something you can see. And so this device here, it's actually assembled as part of the project. The bit at the back is a glass valve which measures the vacuum. The one at the front is a photomultiplier tube which turns the electron beam back into light. In a way I'll explain in just a second. And then finally, you have the viewpoint of glass. And it occurred to us, as it occurred to Catherine in her images, that the final output of an electron microscope, these scan electron microscopes, is onto a glass screen. So what you go through glass and light, a series of steps. The electron beam comes onto the specimen. The electrons bounce off the specimen. It's collected by a little piece of glass with fluorescent dye on it. That emits light. The light goes into the photomultiplier tube, turned back into electricity, which then can be amplified, modulated, sent back to the back of a TV screen, which is again another big thing of glass. And as the electron beams scan back across the inside of the screen, they give you the image that you can see, turn it back into light. So in the end of it, we still have to see the stuff. We've still got to turn the image back into light. So this is how it works. It's like a whisper. When she rests her arm lank across my own, kisses the nape of my neck, sweeps my hair from her eyes, until we might dream of tropical waves rippling our ankle shadows, until we imagine row after row of thunderheads rebuilding our horizons. Later, it's soaring tenor saxophones and hi-hat cymbals, and a rhythm too flexible for us to grasp, while my pulse races towards an unrecognised target 3 beats at a time. And again, she whispers. A hint, a clue. Should I log the days I miss, record the objects I fail to see, the items I place absent-mindedly to one side? Softly she laughs, and I hesitate. Is there something else? Something else I should consider? A button to press? A gauge to read? Her voice remains insistent inside my ear, veils the flickering screen, draws all I think I understand to a single point of anticipation.
Hello everybody. First I would like to thank Jessica for inviting me to this wonderful conference. I'm really happy to be here, feel very inspired, heard already such amazing talks. And I'm working now with glass for 30 years, and I always knew it's an amazing material, but now I think it's an even more amazing material. And so I would like to start with really a little bit of a personal story, so my path to glass. So I was born in Jena, small city in Germany, where they invented the optical glass. So what happened there in the 19th century? The 3 guys, Otto Schott, the glass chemist, Ernst Abbe, the physicist, and Carl Zeiss, the mechanic and entrepreneur, they worked together. They created new optical microscopes and also So these guys then together, they founded the two companies, Shot Glass Company and Carl Zeiss, and they're still out there. So I didn't grow up in Jena. I grew up in a village 300 kilometers north of Jena. But when it came that I wanted to study chemistry, I thought I go back to Jena. And being there for 1 year, at the end of my first year studying chemistry, someone from the Institute of Glass Chemistry asked me if I would like to do a summer project and earn a little bit of money on the side. And I thought, oh, that's a good thing. And so I got really, since then, I'm working with glass. So it really determined my career and my passion. For a long time, I only did glass science. And 3 years ago, it was initiated by Tanya Monroe, an exhibition of our institute together with glass artists at the Gem Factory. And this was in 2011. And then I always thought, I won't like to go back to the glass artist, but being so busy, always postponed. Therefore, I'm so glad now that Jessica invited me, and let's see if I now can hang on a little bit more to glass art. So my talk is really in 3 parts. First, a little bit about the science behind glass, then how we, that means the scientists, make glass and glass art by mistake, and use of the glass to measure the world. So what is glass? Glass, one way to look at glass, it's a frozen in liquid. And what makes glass so amazing, why we can do the art with it, is that it changes gradually from being liquid so that we can cast it. Then it becomes soft so that we can draw it, stretch it. And then in the end it becomes solid material, which we then can show at art exhibitions, or we have the objectives in microscopes. That's very different to crystals, because they change very suddenly from being, so the melt changes suddenly from liquidus to solid. An example is water and ice. So at 0 degrees, we have the change from the liquid water to the solid ice. This is shown here in a scientific way. Where you have here, if you start, so here's a property, it doesn't really matter which one it is, and here's the temperature. So if you have a melt, what's happening? You cool down the melt. If you have a crystal, at the melting temperature of the crystal or the crystallization temperature, you have a sudden change in the property, and then again, sort of gradual change. This is not happening with a glass melt. What's happening there? It continues the gradual change, goes then through the glass transformation region. You already heard about it today, and then again it cools down further. So what's really happening? Here you have the structure of the liquid, which is sort of a random distribution of the atoms in the liquid. And this randomness is is preserved in the glass structure, which is different to the crystals, where at this point here, the components, the atoms in the liquid, they form an irregular arrangement of atoms, and they are then the crystals. So one very important properties of glass is the viscosity. That is the change of the glass viscosity with temperature. And so here I looked at important regions. Here, so this is here a scale of the viscosity. If you have -2, this is the viscosity of water. And if you have here the viscosity there, you have a value of 40, and this is really a solid. And so you can see that the glass gradually changes the viscosity over this wide range of viscosities. And so where we work in terms of extrusion and fiber drawing, where you also work in terms of blowing glass and doing all sorts of unimaginable things for me with the glass, this is the soft glass or the working range. And then down here you have the range where you can cast glass. And here I've shown the viscosity curves for 3 types of glasses. One is pure silica, lead silicate glass, and one of our special glasses, the Telluride glass. You see that these glasses really, they differ in their slope. That means how the viscosity changes with temperature. And so if we see here the silica glass, you have a huge temperature range where you can work with the glass. To a degree, it's similar with lead silicate glasses, but the challenge with our glasses is really that you can see how small is the temperature range where we can do something with the glass. And so therefore these glasses then are called the short glasses. These are the long glasses because they have a long window in terms of time working with the glass. Heike already gave a fantastic talk about refractive index, so I can keep it very short. So I found on the internet this nice image. It's not glass, it's a polymer, but has the same index as standard glass, showing what refraction means. What I put on top of it is the low index glasses window pane with an index of 1.5, and we make high index glasses, or we buy commercial high index glasses, for example, lead silicate glasses. We have then a larger degree of refraction. As I said, window pane has an index of 1.5. Commercial lead silicate glasses, so we work with them quite a lot in the range of 1.6 to 1.8. But we also can make very high index glasses, so the Telluride glass, one particular glass, we can achieve 2.2 refractive index, which already comes very close to diamond with an index of 2.4. I want to talk a little bit about colored glasses, but only about one type of creating colored glasses. That's the type where you have nanoparticles or colloids in the glass. Nano means really 1 million of a millimeter. And so, also in the previous talk, we saw this fantastic piece of the Leucurgus cup. In fact, it's a mixture of silver and gold colloids in this fantastic cup. So this was already done 2,000 years ago. People knew how to make fantastic glasses. Then in the 17th century, they developed the gold ruby glass. Then Zsigmondy, he really figured out what is the reason for the color of the glass. That's the gold colloids or gold nanoparticles. And he won a Nobel Prize for this. So how are these glasses made? So what's happening is that one first makes a glass which has precursors. So the glass doesn't have the nanocrystals yet, but precursors that can then be formed into the nanoparticles. For example, glass that contains gold ions. Gold ions themselves, they don't have any color, and so therefore one can achieve a colorless glass. Then in the heating treatment, or as glass artists say, in the striking, then the gold ions are turned into gold atoms, and then they grow into nanoparticles, and then they create this beautiful color. And there are many other nanoparticles in glass that cause different colors. So also other ingredients are silver nanoparticles, copper nanoparticles, cadmium sulfide, cadmium selenide. And so what really makes these colors so interesting is that the color is sensitive to the nanocrystal size. So depending if you have 20 nanometer or 50 nanometer nanoparticles in the glass, and different color is obtained. And also the which nanocrystal size in the end is formed in the glass is very sensitive to the glass composition and also to the annealing treatment. That means how the striking is done. That of course makes it very hard to control nanoparticle size and concentration. And scientists are control freaks. We want to have absolute control of the processes. And so therefore, 3-4 years ago, in collaboration with a few people or so, we came up with a new concept. And so we start with having already the nanocrystals made. In this case, it's nano diamond, again in the order of 50 nanometer. We make a clear glass melt, and then we throw the nano diamond into the glass. stirred for 3 to 10 minutes, and then we cast it. And so in this way, we can then achieve a glass which contains the nanodiamond. And the work or the billet you see here is relatively clear because we only put in a little bit of nanodiamond. And this was also 3 years' work to make it look transparent. And I come to this more in the next slide. But so that you really can see here a confocal microscope image showing here all the nanocrystals which show a very particular fluorescence. And so they are then under the confocal microscope lit up. So I would like to come back to the Locogus cup. So you have the red color in transmission because then you see the absorption from the nanoparticles, and in the reflection then you see the light that is back reflected from the nanoparticles. And so the first nanodiamond doped telluride glasses I made, they looked like this. And so I was really struck what's going on, because in transmission it looked blue, and then in reflection it had this not so nice sort of ugly color. And because I knew that we made our telluride glasses in gold crucibles, but I was so used to the ruby glass, to the red color, until going through the literature that it then dawned to me is that the ruby glass is a silicate-based glass, has a refractive index of 1.5. Now telluride glasses have a refractive index of roughly 2.0, and that shifts the absorption of the nanoparticles and therefore also the color we can see with it. And so then you have seen in the previous slide that we managed then to make a colorless glass. What it really meant is to perfect the process so that we minimize the solution or dissolution of gold from the crucible. So now a few slides how we make our glasses. So we use also furnaces, melting furnace, annealing furnace, but they are attached to a glove box so that again we can control the atmosphere the glasses are made. Apart from this, everything is the same, the batching, the melting, the casting and the annealing, but it's done under controlled atmosphere so that we can play with the redox conditions in the glass and also to protect the glass from the moisture in the air. So, in this way we can develop new glasses that would not be possible, melting them in open air. And very important, if we want to make glasses that transmit heat, that we need so-called dry glasses that don't contain water. So once we made these glass billets, glass cylinders, then we go into the next process, which is the extrusion, which means we squeeze the glass billet at elevated temperature when the glass is soft through a metallic structure, so-called extrusion die. And depending on the structure of the die exit, sort of imprint the structure into the glass, and we obtain holes in the glass that run along the whole length of the preform. And here you see the machine, which in fact is a metals testing machine. I went to the company and said, I want to have a hole in here because I want to use it for extrusion. It took me a while to persuade them to do it, but they did it in the end. And here you see a few examples of successfully extruded glass pieces with different arrays of holes. So these are all macroscopic pieces where you can see the holes with the naked eye. Here you see a scale bar here, so this is 3 millimeter. This is all in the millimeter scale. Here now you see a few examples of failures, but usually failures look very beautiful. And also these photographs are done by professional photographers, which also then had the light coming from the right angle so that the beauty of the objects really comes through. And so this is our sphere. There was something obviously wrong with the flow behavior when the glass was flowing through the die and caused stick-slip behavior. That's not really useful to make an optical fiber, but it looks good. With this one, the furnace profile was not even, so there was a cold place in the furnace, and therefore when the piece came out of the die, it just bent toward the cold part of the furnace, and then it started to coil up. And here the holes looks very regular, but it looked a little bit different to what I wanted to achieve according to the die design. Okay, now to the third step, what we are doing. Now we take the preform, place it again in a furnace. Now only a small part of the glass is heated up, and then it's stretched out to fibers that are as thin as a hair. And here, because now we stretch the glass, we want to get 500 meter fiber or kilometer fiber, therefore the equipment gets taller and taller. So we have a 4 meter and a 6 meter drawing tower. Here you see a photograph of the beginning of the process, that the drop of glass is coming down, and now you have in between the preform and the drop, there you have the start of the fiber drawing, so fiber is emerging. Here you see a few examples of the fiber structures we make. So we can preserve the holes that are in the preforms in the fibers. Now all these images, they are electron microscope images, which is a very nice continuation to the previous talk. And here now the scales are quite different. Some of these structures, they are just visible in an optical microscope. But some of these structures here, you have a hole with 20 nanometer in diameter, so really an electron microscope is required to see them. What I really like with my work, all these structures, some guide light better than others, but no matter how good they are in terms of light guidance, they all look beautiful. And so therefore, every time that we make a new fiber, and then I see it under an optical microscope or electron microscope, it's just so nice to look at. Now just a few slides on how we use our glass fibers to measure the world. So you see here a fiber, you have seen the structure before. So the black areas are air holes, and the gray areas here and here, it's glass. So what's happening? Because of the index contrast, total internal reflection, that's very nice, we already learned about it today, is now happening in this glass core. So the light is traveling along the glass core, but the glass core is so small that it acts as a rail of light. It is shown here in this animation, so that part of the light is outside of the glass and goes into the air hole. Now imagine the air holes are filled with a liquid, with something we want to measure, and now we can have an interaction of the light with the matter that is located into the air holes. This is shown here, an optical fiber with these holes dipped into a solution, and then via interaction of the light with the matter in here, and also having an excitation laser beam, we create then a signal, which is then back reflected into the fiber, travels along the fiber to the detector. And so if this newly created light signal gets stronger in intensity, then we know that a certain chemical we want to measure is in higher concentration than in this liquid. What is really the advantage of these fibers is you can see how small they are, and therefore we only need to take very small sample volume. And this is where the project with the embryo sensing comes into play, because we don't want to disturb the embryo, but nevertheless measure what chemicals are situated in the solution where the embryos are sitting in. And with fibers, we only need to draw a minute amount of sample fluid. Then another quite different example of what we can do with our fibers. In this case, the fibers only to transport the light to and from these microspheres. And in the microspheres, I just love it, it looks so nice. There you have these so-called whispery gallery modes. So light is just traveling along the outside of the microspheres, and how this light travels there is so affected by the environment that if now a chemical comes close to the surface, it changes how this light is traveling there, and this can be used to sense the environment of the microscope. Half a year ago, we are privileged to be part of the Center for Nanoscale Biophotonics, and this center is really about using the optical fibers to measure nanoscale phenomena from a distance. So that our ultimate goal is really to use the fibers to see what's going on in our bodies, to understand, I guess, how life works. And so we have the three themes. Once I already mentioned it, spark of light, how does life starts. We want to look into our blood vessels, just because they are plugged in our blood vessels, but there are good ones and bad ones. At the moment, I can't really distinguish. So hopefully with our fiber sensors, we can figure out what are the bad plugs, and then they can be removed before people have a heart attack. And also we want to understand what's going on in our brain when we feel sensation, for example, when we feel pain. So my last slide. I would like to thank many funding sponsors so that I can do this amazing work. In particular, I would like to mention the Australian Research Council and also the South Australian State Government. This last slide here, so many people inspired me, but I feel these three people, they really made a difference to my life. So Doris Eert, she really was my supervisor, my PhD supervisor. And so she got me in contact with neodymium-doped glasses, these wonderful reddish-looking glasses. Then in 2003, I got to know Tanya Monroe when I was over at the University of Southampton. And there she asked me if I want to do something with glass extrusion. And so I got to know the extrusion. It's like with the glass itself, I can't let go. I find it such a fascinating technique. Also, she introduced me to the wonderful world of micro and nanostructured fibers. And recently now I'm introduced to Mark Hutchinson. He's the interim director of the center, and he really inspires me in terms of what we can do with our fibers. So he's looking into the brain, what's happening when we have sensations. And I thank you for your attention.
Thank you so much. I was so inspired by all three of your talks that I'm almost speechless. But I also now understand, thanks to Heike, some phenomena that are going into a piece that I've just recently finished in the exhibition Translucent Shadows. So I just think it's absolutely fabulous as someone who works in material, and also often get too focused on their own stuff. To be able to have all of you here, for us as artists to step back and look at the actual material that we're working with in a wider sphere. So thank you very much. I've just got a couple of announcements before we break for afternoon tea. Just to please check the blackboard, and the blackboard is at registration for any announcements, particularly from our site. And also, if you are donating to the auction, which I'm sure you all are, Denise is the person to see at the registration desk. And also, the conference exhibition at Worth Gallery closes today at 5 p.m. And this is also when votes have to be in for the Vicky Tour out $8,000 prize. So please make sure you all put your vote in for that. So morning tea is in the foyer. Sorry, afternoon tea. Oh, I nearly did it all correctly. And then we have a few other great sessions for you here after that. Thank you. Thanks very much.